if we talk about engineering, it happened, it considered in electrical appliances that produce um, noise, noise. And then in civil engineering, we also concerned about acoustic, for example, the traffic noise, the construction site, and also room acoustic, or noise in the classroom or in the room, or in, for example, in the seminar room and so on. So that is part of acoustic. So we need to consider it in our construction. Okay. So these books talk about acoustic. For example, we have a special book on the opera house. This one is urban sound environment. And also this one is our books from the construction noise. So there are a lot of books you can find in the internet or in the library. So if you have time, feel free to read it. Okay, this is the book that concern on the construction noise. The first book related to the construction noise. But now this book we stopped the printing because of the COVID-19. But for the next week, I will try to give you some of the the gist of the book. Okay, when we talk about noise, maybe we have a lot of noise problem. For example, noise may happen in the room, in the office, due to traffic noise and so on. So to tackle the traffic noise, to tackle the noise problem, you need to understand what is the source of the noise. Does someone want to join? Badam Zul. Okay, for example, if it is happen in the room, so what standard we need to refer, and what is the parameter that we concern is different from the traffic noise. For example, if you annoyed by the traffic noise, so what is the parameter we need to consider, or how to reduce it also different compared to the noise in the classroom or in the office. So therefore, to understand that, I have listed in a chart here the problem of acoustic. Sometimes a problem happen due to environmental. For example, traffic noise. It is happen due to the car, due to the transportation. So it is called environmental noise. And to reduce it, we need to refer to the Department of Environment, Department of Environment Malaysia, or highway standard. We have also highway standard. Or you can refer to the regulation from UK or from US. Okay. Okay. If, for example, construction noise, so we have different from the traffic noise. We need to refer to the DOE, but if you are concerned about the workers, so we need to refer to the different code. So we can see here, and then the code, maybe we can refer to British code BS 5228. So we have, for example, here 3 code we need to refer, but for the traffic noise, we just refer to the DOE. For another noise, maybe neighborhood noise. So that one we need to refer to WHO or DOE. So we need to consider what is the source and what is our problem categorized. All right. For the second one, for example, it is in the building. For example, in the office, in the school, in the auditorium, seminar, and so on. So the parameter also differ from the environmental noise. For example, we need to refer background noise and also reverberation. Yeah, I will explain it to you later. And then if in the factory, so we need also different from the traffic noise. We need to refer different standard. In a factory, for example, we may concern with the factory, the workers, the workers in the factory. So we need to refer to the OSH 2019. Yeah? So you can see here from the diagram, the parameter that we concern is different from the, if we compare, if the problem arises in the environmental and also in the building. Yeah? So we need to understand what is our problem actually based on. Is it in the environment or is it in the building? Yeah, when we talk about noise problem, so we must consider what is the main source. Yeah? So what we concern here is actually we commit with the Agenda 2030 that is moving toward the Sustainable Development Goals. So I think most of you have already know what is the sustainable goal, the Sustainable Development Goal. So we have many SDG, right? So for the noise, we have three categories that we concern. The first is SDG 3, that is health and well-being. Yeah. The second one is SDG 4, quality education. Yeah. And the last one is SDG 9, sustainable infrastructures. Yeah. So most of our problem arising from the noise problem, yeah, is actually we try to fulfill the sustainable development goal, yeah, through the SDG 3, SDG 4, and SDG 9. Acoustic actually is a branch of physics. Yeah? We need to study what is the, we study the physical of sound, we study how they produce, how they propagate, how they transmit, yeah? What is the impact to the receptors, and also effect to the human, yeah? As well as the animals. Yeah? That is called acoustic. Yeah? That is the, we study the sound, physical of sound, the production, control, transmission. Yeah? That is called acoustic. Yeah? So it is actually is fundamental to many developments of the technology today. Yeah? For example, the a lot of things, yeah, in the medicine and also in the engineering. Yeah? So finally, acoustic can be divided into two, yeah, that is sound and vibration. So our concern for this course is the sound. Yeah? Okay. So now we go to the next one. That is physical of sound. Yeah? Just now I have mentioned that acoustic is related to sound, physical of sound. Yeah? Therefore, if you have a noise problem, we must know, we must determine first, and we must relate the our problem with the physical of sound. So this lecture content of 4 important things, important objective here: fundamental of sound, B, sound power. Yeah, I will talk about sound power. The next is this sound propagation, how sound propagate. Yeah. And the last one, this should be D, formula for sound calculation. Yeah. So this is the most important part of the physical of sound. Okay, the first one, we need to study what is the physical of sound. So here is the picture of the things that produce sound that you normally, the first one is the guitar, acoustic guitar. When you talk about acoustic, you may you may think about guitar. Yeah, this is the bell and this is the drum. Yes? All of this produce sound. Yeah? Good sound, I mean. Yeah? The guitar is a good sound, that sound that you desire. Yeah? Also the drum. Okay, so fundamentally it's actually sound produced by the compression and also condensation of the air molecule. Yeah, you can see here, if we clap your hand or we use fork, yeah, the air will be compressed. Yeah, compressed. You can see from the diagram, the bold one is the compressed and the light color is the refraction. It's just like structures. When we put a load, there's a tension and compression. It's similar with this one. So when this molecule move to our ears, it will enter to the ear canal, then goes to the our ear, inside ear, and then this is the cochlea that decide what it is it loud or it is annoy the people that hear the sound. Okay, this movement will form sound wave. Okay, so if you, let's say, make sound using a fork, for example, it will create a pure sound. Pure sound. It's happen usually in a music note. It is. It has a sinus form of wave, cos or sine. This is cos or sine wave. Yeah, this is usually happen for the musical note, and this sound is not produce annoyance to our ears. Okay, on the other hand, if you use hammer to produce sound, you will find that the wave is not regular. Yeah, it's not like a musical note produce sine or cosine, yeah, with smooth and consistent amplitude. But for the noise produced by the hammer, it's not uniform. Yeah? This one is called noise. Yeah? This is unwanted sound. It is very annoying, yeah, because of the it's produce, it is called tone. Yeah, this is called spike. Yeah? This is called spike. So this is a comparison between musical note and noise. Okay, just now we talked about the pure tone. Yeah, let's say we concern that noise with the pure tone. Yeah, the pure tone, it will produce sine or cosine wave. Yeah, so we need to understand the properties of sound wave. Yeah, this is particularly important for the if you studied about the treatment. Yeah, if you want to develop material to treat the noise, to absorb the sound, to improve the room, or to reduce traffic noise, something like that. Yeah, this is the parameter that we need to understand. Yeah, so first of all, sound will produce the wave. Yeah, so the wave, it has a properties like wavelength. Yeah, you can see here from this peak and this peak, it is called wavelength. Yeah? So the highest, yeah, the distance from the lowest and the highest wave, it's called amplitude. Yeah? This amplitude is actually the value of the sound pressure level. Yeah? If you have a meter, I will explain later. Yeah, if you measure the noise using the sound level meter, yeah, the reading that you obtain is actually represent the amplitude of sound. Yeah, so for a sound with specific frequencies, Yeah, this is the frequent. Yeah, so the wave, it's got a sine wave like this, and how many wave form in 1 second is called frequencies. Yeah, frequencies here, F. We have equation 1 here. Frequencies C is equal the wavelength for 1 cycle here, time frequencies. It is called, it is a produced speed of sound. Yeah. So basically, from the wave, we have a amplitude. Yeah, here amplitude, and between these two peaks, it's called wavelength in 1 cycle. This is 1 cycle. Yeah? 1 cycle. Yeah, so wavelength. Okay, so we develop. So the expression can be established that is C is equal lambda F. Okay, you don't need to remember this. Yeah. But you need to understand the relationship between the speed of sound in the air is equal 340 meter per second. Yeah? So the speed of sound in the air will be different speed of sound in the, for example, in the solid, yeah, this in the wood, yeah. So in the wood, it's maybe higher than the in the air, yeah. So the F here, we call it frequency. Yeah. So this frequency, I think most of you very familiar with the frequency. If you listen to the radio, yeah, for example, era radio, yeah, we got frequency 94.5. Yeah? 94.5 means the number of wavelength, the number of cycle in 1 second. If it is 1000 hertz, your radio got frequency 1000 hertz, meaning that in 1 second it got 1000 cycle like this. Eh? So it got 1 cycle. Yeah. So that's why for the radio, especially, yeah, for the channels, in order not in order for them, each channel did not get crossed. Yeah? So it will, they select one specific frequencies. Yeah? So the frequency that radio use is actually same with the one we talk here. Okay. So this is the wavelength. Yeah? The wavelength is very important if we want to treat the noise in a room. Yeah. Okay. So still with the properties of the wave, yeah, let's say you see here, this is the wave here. If let's say we have the wavelength, yeah, with these frequencies, yeah, you can see here. So this is called amplitude. Yeah, this is amplitude. Amplitude, yeah. Amplitude. Usually we put it as dB, yeah, or pressure, yeah, dB. Okay. So this is amplitude. Okay. By referring to this amplitude, yeah. Okay. If we reduce the amplitude, yeah, we reduce the amplitude. Look at these figures, yeah. But with the same, yeah, the same cycle. Okay. Okay. We'll show you here. From here to here is 1 cycle, right? 1 cycle. 1 cycle. Yeah. This is 1 cycle. One cycle. Y cycle with the length lambda L. I cannot do this symbol lambda, so I just put L. Okay, by referring to this amplitude, if we change the amplitude, yeah, we make it smaller than this. Yeah. Let's say we have P1 here. The amplitude reduce, yeah, reduce compared with this one, but the length is still same. Yeah. So we can say that the loudness is decreased. The loudness is decreased. But if we increase the amplitude with the same lambda, the same cycle, yeah, the same cycle, so we can call it increase. We increase the loudness. For these figures, yeah, on the other hand, yeah, we call it pitch. Yeah? This one is loudness, yeah? Loud, the strength of sound, right? But this one is pitch. What is pitch? Yeah, pitch related to the length of the lambda, the length of wave. Yeah? Here, look, for the same amplitude, yeah, the same amplitude with this one and this one, the same, yeah, the same amplitude, but we, you know, we stretch the wave, we stretch, make it the wavelength larger. Yeah. So this one we call pitch increase. It's called pitch, meaning that the sharpness of the sound. Yeah? This one is loudness. This is sharpness. Yeah, the sharp of the sound. Yeah? So this is the important aspect of acoustic. We have loudness and we have the pitch. Yeah? Okay, don't worry about that if you don't understand, still don't understand. Okay, okay. Now, this is our ears. Yeah, actually the sound that come into our ears. Yeah, for example, my voice right now. Yeah, so it is actually comprises of complex sound. Yeah, complex sound. This sound is actually from different frequency, yeah, different frequencies and different amplitude, different pitch. Yeah, so it's combined together. Yeah, here. So we totally up get into our ears. All right. So our you know, our brains, yeah, that will change. Oh, this is loud, this is sharp, and this is very pitchy, something like that. Yeah? The sound comes with complex sound wave, and then our ears that will change it. Yeah? Okay, to single frequencies. Yeah? But with the knowledge, of course. Yeah? All right. So, as I mentioned just now, the sound, yeah, that come from source, any source, it consists of different frequencies. Yeah? For example, you can see here, let me erase first this one. Okay, some sound may produce low frequencies. Yeah? Low frequencies, it's characterized by the here, by the lambda. This is called lambda from here to here. Lambda just now, it is the length of the wave, the length of the wave. For the longer wave here, it is called frequencies. Low frequencies. Low frequencies means it is less than 200. Yeah? From here to here, it is called low frequencies. From here to here, this is called low frequencies. Yeah, meaning that the wave can be ranged between 2 meter, yeah, 2 meter to more than 20 meter. How to get this measurement? Yeah. Okay, the measurement you can get from this formula. This formula, C is equal lambda F. Yeah. So lambda we can calculate by dividing the speed of sound 342 divided by f, frequencies. So what is the frequencies required? You can see from here. For example, 200. Yeah. So you got 242 divided by 200, you can get 1 point something here. Yeah. For 100, so you get value here between this one. If you got the calculator, you can simply calculate. So this is actually the distance represent for each of the frequencies. Therefore, actually for the human, we can hear from 20, from 20 to 20,000. Yeah. This is only 10,000. So we can hear from 20 to 20,000. Yeah? So human can hear the range from 20 hertz to 20,000, but it's depend on your age. If you are younger, then you may hear 20 hertz, 30 hertz, 50 hertz, something like that. Yeah, it clearly then for the older people. Yeah. Okay. So back to our division of frequencies. Yeah. So let us erase this. So the frequencies can be divided into low frequency, mild frequency, and high frequencies. As you can see here, from 200, less than 200 is called low frequencies. Mild frequencies is between 200, more than 200, up to 500 to 1000. This is mild frequencies. And this is the wavelength, 0.5. So 1000, it may be 0.2 meters, something like that. Yeah. So for the higher frequency, you can see the comparison of the shape here. Yeah. The higher the frequency, the lower the wavelength. Yes, you can see the wavelength is very small. Therefore, it's easy to treat. Yeah? For the sound source consisting of high frequencies, it easily can be treated. Yeah. Okay, so for the, let's say 20 hertz, referring to 20 hertz here, let's say if your sound source consists of 20 hertz, so we need 70 meter size of obstacle to cut this noise. Yeah? Yeah, you can imagine how big is 17 meters. Okay, so for the noise barrier, usually it is 4 meter. Yeah, 4 meter about this. So actually for the noise barrier, it can cut sound between 100 hertz to 10,000. Okay, so can see here from this scale, this is the approximation of the wavelength. Yeah, this is the wavelength. Sorry, the wavelength. The wavelength for this one is from cycle to cycle. Easy. Yeah, this one. Or from here to here. This is the length of the wave. Okay. All right. That is wavelength. Now, let us see frequencies. Yeah? As I mentioned just now, sound is made up of a number of frequencies. Yeah? It is from 10, 20 that we can hear, from 20 to 20,000. Yeah. Okay, so let us see the frequencies. go to the YouTube. Okay. Okay, this one is the how the frequencies, yeah. Look at this is 22 hertz. We increase the signal of sound, change between 20 to the highest possible. So you can see here the wave, yeah, the changing of wave. Yeah? Now we looking at 30 hertz. Yeah, it's become yeah, become smaller. The wavelength becomes smaller. You can see here. This is 50 hertz, all right? Okay, still I cannot hear. How about you? Yeah, 72 hertz. This is the range that young people can hear. I think if you are young, you are younger than me. Of course, you can hear this sound right now. Okay, now I can hear. So now it's 500, yeah? So according to the scientists, yeah, traffic noise is very dominant between 500 to 1250. Yeah? So this is the range for the traffic noise. Yeah? Okay, let us feel how loud the sound at 3 to 4K. According to the the wavelength, you cannot see, it's very, you know, okay, reaching to 10,000, it's become less. Yeah? Okay. Okay. 13, 14, yeah. You can see the wavelength now become very smaller, very small. Eh? Okay. Okay. Okay, I want to get out from here. Right. Okay, that is the noise spectrum. We call it noise spectrum. Yeah. So actually, the sound we human hear from 20 to 20,000. Just now you already hear, yeah, the loud, how loud the sound for each frequency is, right? And also see how the variation of the wavelength from 20 to 20,000. Yeah. So for the human, it is 20 to 20,000. But for the animal, maybe the range is bigger than that. Yeah. Okay. So the scientist says that our ears is very sensitive, 3 to 4,000. Yeah. That's why if you are workers in a noisy factory, something like that, yeah, OS will, you know, test, yeah, your hearing, and they will, you know, get the what do you call, to the audiometric test, audiometric test, and if the doctor found that your 3 to 4,000, yeah, you know, very disturbed, then they will give you, you know, like what do you call that? Compensation, yeah, compensation. You are, you know, you can get compensation from the SOCSO, yeah, and you are also entitled with the special hearing device. Yeah? Okay, so now back to our noise spectrum. Yeah, for the, since the range of spectrum is so wide, yeah, so engineers have split them into, we call it center octave band. What is center octave band? This is called center octave band. That is 3, 1.5, 63, 125, 250, 500, 1000, 2000, and 8000 here. It is called center octave band. Yeah. So as you can see just now, the wavelength, yeah, due to wavelength and due to the amplitude, so the measurement, yeah, the loudness from each of the frequencies will be different. Yeah? For example, here 31.5, it's lower than 63. Yeah, so this is the nature of the sound. Yeah? So each sound source will produce different graph like this. Yeah? Okay, so if you still don't understand about the sound, yeah, can you think about the prism last time in your Form 3? Yeah? You studied about the rainbow last time in a Form 3 or Form 2. I still remembered. Yeah, we given prism by the teacher, and if we put the white light through the prism, we will, you know, produce several colors here through this prism. It's like a magic. So in a sound, it's also like that. We have a sound level meter that I will show you later. By using the sound level meter, you will get a lot of frequencies of sound. For example, if my voice, yeah, I measure it with the sound level meter, so I can get my voice is actually consisting of different frequencies. Different frequencies. It's just like different colors like this. For example, 31.5 is, you know, with this color, 63 with blue, and so on. It's just like a rainbow, rainbow color. Okay, now again, yeah, sound consists of different frequencies. Yeah? This is the frequencies, original frequencies, yeah? From 20 to 20,000. Yeah? So now engineers, as I said just now, we can divide it into octave band or 1/3 octave band. Yeah? Beside octave band, we also use 1/3 octave band. Yeah? So octave, 1/3 octave band is usually used for the engineering purpose. For example, for the treatment of room, treatment for the traffic noise. We need to study the content of 1/3 octave band. Now, what is 1/3 octave band? I will show it later. Yeah? So in conclusion, yeah, our human range, although maybe, yeah, it can consist more than this range. Yeah? So for the lower than 20, we cannot hear. Yeah? For example, it's called infrasound. Infrasound that used by the, to detect, to scan the, baby in a woman, pregnant woman. Yeah, it also used the sound technology less than 20 hertz. Yeah, it's called ultrasound. Yeah, less than 20. This is 20 is considered as low frequency. Lower than 20, it's called infrasound. Yeah. So our most sensitive is 2,000 to 4,000, and we can compare. Yeah, the dog can hear up to 30,000. Yeah. So therefore, actually, yeah, you can see animal. If you got the cat or dog in your house, you can you can try to understand them. Yeah? Actually, they are talking to each other, but using the frequency that we don't hear. For example, maybe they talk about more than 20. Yeah? More than 20. Yeah? You can see, I got a cat here in my house. Yeah? I can see when we, give a food for certain, for one cat, yeah, the other cat will, like talk to each other and ask them to eat as well. So it shows that they are talking. But we cannot hear their talk. They are talking. Okay, that is the about the frequencies. I hope you understand, yeah, the basic of the physical of sound. Okay, now this is from the WIS 2001. Actually, the curve here is called phone curve. This is curve here is called phone curve. It is invented by the Fletcher and Manson back in 1900. Yeah, they studied about the sound, how people perceive sound. Yeah. To produce this graph, they have experiment. They did experiment on the young people. Young people means people with age less than 25 years old. And they produce the sound. For example, pure tone. Pure tone. You have heard pure tone just now. How the pure tone from the YouTube just now, we call it pure tone. That is sound at particular frequencies. Yeah? So they experiment the young people in the lab, and this graph shows the loudness. the same loudness. This graph shows the same loudness. You can see here that, for example, normal threshold of hearing means the lowest that people can hear. This is this line, it shows the lowest people can hear. Yeah? For example, here is 20, 30, 40, and 50 hertz. This is frequencies. Yeah? At 20 and 20 hertz, yeah, we can hear if the sound level is 20 dB, 70 dB here. Yeah, and it got same loudness if at 1000 hertz with only less than 5 dB. Yeah? 5 dB at 1000 got same loudness, same as 70 dB, 70 more than 70 dB here at 20 dB. Yeah. So you can see that our ears, it's actually not sensitive to the lower sound, lower frequencies. It reduces, yeah, until, you know, it's not sensitive at 10 dB, and then getting sensitive slowly until here 5 to 5,000, 1,000, 2,000, 3,000, 4,000. They're the most sensitive here. Yeah, it's negative. Yeah, it can see here negative, meaning that very low pressure here at 4,000. Yeah? And getting less sensitive to the higher sound. Yeah, you can see just now. You can feel just now from the example from the YouTube. Yeah? You can feel very sensitive, getting sensitive, and then suddenly you cannot feel anything at nearly to 10,000, right? So this is called zero phone. Yeah, and then at by referring at 1000, how they put 20, 40, 60, 80, 100, and 120 is based on 1000. Yeah? If at 1000 the reading is, we consider zero here, this is called zero. We consider here zero, although it is not actually zero. And then at 20, yeah, this is called 20 phone. Yeah? The line here, the whole line at 20 dB at 1000, it's called, which got same loudness at 20 dB at 1000. Yeah, it's called 20 phone. This is the same loudness. Yeah, and then 1000 with 40 dB here, which is called 40 phone. Yeah, and we can draw the same loudness as 40 dB at 1000. Yeah? You can see here from the experiment, it's turned like this. Yeah, so it's, yeah, it's accordingly 60, 80, 100, and 120. Yeah, this is the threshold pain here. Yeah, you cannot receive greater than 120 dB. Yeah, at 1000. Beyond this, you will get your ears damaged. Yeah, okay. So this graph also shows you the activities that produce the loudness, yeah? The similar loudness here. Let's say for 60, 1060 dB. Yeah. So the activity that produces 60 dB is people talking to each other. Yeah. For example, my voice here may be 60 dB to 70 dB. Yeah. And then you got maybe here compressor. Yeah. I don't know. It is compressor. Yeah? It's bird chirp, bird here. But chipping, yeah, in between 50 dB. Yep, people who play piano, yeah, it's between 60 to 80, maybe 75 dB, something like that. Yep. If you are using the vacuum cleaner, it is 80 dB. Yeah? The car 80, the truck also 80. Yeah? 80, but dominant at 50 hertz. Yeah, 50 hertz. Yeah, the location of this, yeah, the location of the noise source shows that they are dominant source. Yeah? For example, for people talking at 60 dB. It is usually at 500 hertz. Yeah? People more using the vacuum cleaner here. Yeah, the maximum reading is at 600 hertz, 500, 600 hertz. So it produced 80 dB. Yeah, so you can see a different noise source here. This is called noise source with different dominant level. It is called dominant. Although we have although let's say I'm talking now, yeah, my voice is produced from different frequencies, but the main that dominant is at 500, something like that. Yeah. Also, for example, for drilling, yeah? Activity for the drilling here. Yeah, drilling, it's dominant at 4,000. Yeah? 4,000 here. 4,000. Okay. Although the drilling may consist of a lot of different frequencies, the main that the dominant is at 4,000. That's why, yeah, for the workers, yeah, 4,000 is the critical frequencies. Yeah? All right. All right. So we go to the second part. Yeah? Sound power level. Okay. So what is sound power level? So you have seen here, yeah, the source of noise, some of the source of noise in this diagram. Yeah, we can see a vacuum cleaner, yeah, okay, the truck, the car, and so on. Yeah? They produce the noise. Yeah? So the thing that produce noise, we call it as sound, is the noise source. Yeah? So the noise source, for example, here, well, in the construction site, we have a lot of plants. Yeah? So each plant is a noise source. For example, here this is a tractor. Yeah, this tractor, yeah, when we bought the tractor, new tractor, the manufacturer will give you the intensity of the intensity, that noise that will produce by the tractor will be given in the sheet given. Yeah, you bought the new tractor, then they will inform you the specification, inform you the watt, yeah, the watt, acoustic watt, and also the power of the acoustic. So the power of the acoustic, usually they will mention in watt or dB. And some the new plan, yeah, they provide the dB. Some usually, yeah, they will put the dB, yeah, the acoustic power. Yeah. Not only the plant. Yeah. Air conditioner also, yeah? AC system also. If you bought the new one, try look at their spec. They will explain to you, they will state that your aircon may produce how many dB. Yeah? So that is very important, yeah, for the acoustic consideration. Yeah? Okay, so the plant, yeah, will produce sound power. We call it sound power. The unit is watts or dB. Sometimes the book uses the terminology PWL or WL. So in my lecture, I will use LW. Yeah. So how to measure the sound power? Yeah. This is how to measure. Yeah. According to the ISO, yeah, we have a 10 point. Yeah. 10 point around the source. So I don't want to teach you how to measure. So I just want to share with you what is the sound power. From this reading for each point, we average it, so we get sound power. Yeah? Okay. Now we have this formula. LW is equal 10 log 10 W over W naught. Yeah? So do not worry with this equation. Yeah. Yeah. So actually, sound power, yeah, can be obtained. Yeah, sound power level, as I mentioned just now, if you bought plant, sometimes they provide you the sound power level in dB, but sometimes do not. They only give you watt. If they give watt, if the spec only given you watt, then you can use this formula to get the sound power level in dB. For example, pneumatic drill has 1 watt. 1 watt. So what is this, the loudness of the machine, the pneumatic drill? You cannot imagine because it is watt. So you can change it using this formula, by inputting 1 watt into this formula, with reference watt. This is reference 10 to the minus 12. So you can get the reading of 120 dB. So you get 120 dB. So for your information, our voice radiates, it is 0.0002 watts. It's very small. Okay. So what's here is the concept is the same like the bulb, the lamp, the bulb. Okay. Okay. So this is sound level meter. This is, let's say we have a machine here. So usually we will monitor the noise that produced by the construction machine. And normally they will produce at a specified distance. For example, 1 meter, 2 meter, and so on. For the 1 meter, for the simplification, 1 meter, we call it as sound power. So this is sound power. Okay, so our measurement can be in reading, in reading Z. Z. So this is the frequency. Just now I showed you the frequency reading. So the frequency can be in Z reading, the unit Z, the unit A, and the unit C. So what is the difference between these three? Z reading, Z reading is the reading that without taking into account sensitiveness of our ears. That is called Z reading. It is like when we design a building, we will consider load. The load we consider in the building without safety factor, we call it as characteristic load. So it's the same here. If you measure without taking into account our ear sensitivity, it is called Z reading. It's also measured in the frequency. Sorry, I need to mute. If I need to mute, okay. 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 So if we consider our ears, our health, so we need to read in dBA. So it's different. The same reading, if we put factor, then it become like this. It's low at the low frequency. You can see here the difference without factor and with factor here. And this is the reading in C. C means the reading from the machine itself. It's different from this. Okay, so how to get this reading, I will tell you later. But the important thing in our course is the dBA. It considered our sensitiveness to noise, to our ears. So it's called dBA. Okay, how to get that reading? So that reading can be obtained if we use sound level meter. Sound level meter. This sound level meter can be divided into two types. The first type is called type 1. Type 1 is a very high class in sound level meter category. Yeah, it can read, it can measure the Z, yeah, the Z reading, the A reading, and also C reading. However, for type 2, yeah, type 2, we got to type 2 here, for example, pulsar here, we got in our lab, yeah. It is only measured in type reading dBA, yeah. It's only reading dBA without showing the frequencies. Yeah? So because of that, type 1 is expensive than type 2. So if you want to measure noise, yeah, for the treatment, so we better use type 1. Yeah? This type 2 can be used for the measurement, normal measurement. Yeah. Okay. Okay. Since now we are PKP, you cannot see you cannot hold the sound level meter in the lab, yeah. But don't worry, yeah. I think most of you have smartphone, right? So your smartphone also can you know, measure the noise using the apps in the smartphone, yeah. So you can go to the Play Store, yeah. But the reading, yeah, the reading is not as accurate as the sound level meter, yeah. Okay, let's see here, yeah. Okay, this is my phone, yeah. This is my phone. Okay, now you can see here the name of the app is called Sound Analyzer, DB. Yeah, you can try your phone now. Go to the Play Store, yeah, find Sound Analyzer, yeah, with the symbol, with the DB, yeah, like this, the symbol DB like this. Yeah, download it for free. Yeah. Okay, after you download, okay, now, okay. So you can see here, the apps, it has a SLM. SLM means sound level meter with statistic function. Yeah. You also can measure its spectrum analyzer. Spectrum analyzer means you can get the reading from the frequency that you learned just now. Yeah. And this is the calibration. Yeah. Okay, calibration. You can also calibrate. Yeah. To get the accurate data, you can calibrate, but you need to calibrate with the SLM. Okay. Now, to use this, now for the SLM, yeah, you can get the reading. Statistic means average, fast average. Yeah, this is called statistics. I will explain later or next week. Yeah, for the statistic for the SLM. Yeah. Okay. Let us see how they can read. Yeah. Okay. So they produce the LA min, L max. This is called the average sound level. The minimum, the maximum, yeah, and then the average between L min and L max is got average. Okay. Okay. Now, if you don't want to get the info about the frequency, you can use just SLM. Yeah? It will give you data about this statistic. Yeah. Right. But now, if you want spectrum, okay. Now spectrum, Okay, as I mentioned just now, if you want to get detail about your sound, the frequency, 1/3 octave band, 1 octave band, the A weighting, and so on. So you can choose spectrum. Yeah. For example, now I choose this is 1/3 octave band. Yeah? You can press 1/3 octave band. So it will record. Yeah, it will record the reading. Yeah? For example, this is my house. Yeah, the reading at my house. So I can get now the reading since this is octave band. Yeah. So you can see the reading up and down for each frequencies. Yeah? Okay. All right. Let's say this one is Z weighting. Z weighting without any factor. Yeah. This is the original measurement of sound. Yeah. Okay. It's up and down. Yeah. Let's say now I choose C. Yeah. It's a bit different. Okay. Now I want to choose, if I choose A. Yeah. A is taking account the sensitivity of our ears. Yeah. All right. Then if the info about one octave band. Yeah. Okay. Now this is the calibration. If you want to do the calibration, we need sound level meter since you don't have sound level meter. Yeah. So you cannot calibrate. Yeah. Okay. Okay. The advantage of this app is that you can save it. You can take the reading. Yeah. So if you want to take the reading, yeah, you need to press. Sorry. Okay, let's say now. Okay. This is 1/3. Okay, now, if you want to take the reading, just press stop. Press stop. Okay. Press stop. Then, okay, not yet. Okay. You can send it through Telegram or WhatsApp. The data will be sent to WhatsApp. Now I choose WhatsApp. I send to my daughter, then here. Yeah, my reading here. And then you can read all the reading in Excel format. Yeah? So that is the advantage of the advantage of the sound analyzer. Yeah. Beside this sound analyzer, you can also get another apps, but this is the best apps that I can find in the apps right now. Yeah. And it imitated the sound level meter. Yeah. Okay. Okay. Okay, I have mentioned just now about the loudness curve. Yeah? So, since our ears capability of hearing sound is very limited, yeah, we don't want this part. This part we don't sensitive at the low frequencies. Yeah? You can see from the graph here, our sensitivity to the lower frequency is very, very weak. Yeah? But we very sensitive at 2 to 5K, 2 to 4K here. Yeah, because you can see here the curve here. It got deep here. Yeah. Therefore, 40 curve here. Yeah. Scientists has developed a correction, a correction to the original reading of sound. Yeah? So we can modify it to take into account our ear sensitivity by correcting with the curve 40. This curve, yeah, this curve, we take this curve and we invert it. Yeah, here. This one, A weighting. This is the correction. The C weighting is actually only important if we want to find the peak noise. Yeah? Therefore, for the peak noise, usually we will refer LC peak. L mean level, C mean C weighting. Yeah? Z mean Z without weighting. It's called Z weighting. This is the one that we consider A weighting, that human are, that representing the capable of human hearing, yeah, A weighting. Okay, this curve, yeah, we transform it into the data here. Yeah, this is the correction that we need to take into account. Yeah. So frequencies, this is the frequencies, this is the column of frequencies. Yeah, so for the frequency 20, we need the correction of minus 50.5, yeah, to 25, 44.7, and so on until 2000. This reading is actually to correct this one, yeah, to correct this portion, this portion, okay? Okay, example one, yeah, this example. Now, in construction site, yeah, there are a lot of noise source. For example, we have a compressor here. This is the compressor. Okay, if we measure the compressor, yeah, with the sound level meter, just now we measure at 1 meter, yeah, 1 meter distance from this compressor. Okay, let's say we have a octave band reading. Yeah, this is octave band reading I mentioned just now. Octave band is 31.5. Don't worry about this. Yeah, if you have sound level meter, you can choose. Oh, I want the reading in octave band, 1/3, and so on. It's similar with the one that I show you just now, in the smartphone, using the sound analyzer. Yeah? If you want to measure in 1/3, just press 1/3, and it will give you the reading, automatic reading. Yeah. Okay, this is reading. This reading is exact without any, without concern our ears. Yeah? The data in dB, yeah? Meaning that this is taken without applying A or C. Yeah? This is in Z, or in other words, in dB, the original sound. Yeah? So this is the original loudness, the amplitude. Yeah? The value, this value is the amplitude. Remember just now we talked about the, where is my, yeah? Remember just now we talked about the sound wave. Yeah? So this reading is the amplitude, actually amplitude, represent the amplitude. This is the amplitude, okay, the amplitude from 0, yeah, to the, not from here to here, but from 0, the amplitude, yeah, from 0. The amplitude, this is the reading for the amplitude. And this reading amplitude, yeah. So for 31.5 hertz, the amplitude is 124.5. 63 is 120.5, and so on. Yeah. So this, it's called sound pressure level. Yeah. That is the amplitude. Of course, it's not the real amplitude. Yeah. It's normally is 0.7 of the real amplitude. Okay. Therefore, this compressor produce, as measured by the sound level meter, this compressor produce a different reading in each octave band. Yeah? For example, we can see here that the dominant is at 1 to 5. Yeah, you can see here the dominant reading is 1 to 5. Yeah, okay, 1 to 5. Here, 1 to 5. Okay. Right. So the question now is that calculate sound power in dBA for the compressor. Okay. So we have now in each frequencies, octave frequencies, but in unit dB. Now we need to calculate what is dBA. What is in dBA? This one. Yeah. Okay. Now look at the solution. Yeah. Okay. Let us erase first this one. Okay. Now, this is the octave band, yeah? 31.5, 63, 125, and so on. Just copy back this one. And the value for the without in dB, yeah, 124, and so on, you know? Okay, now add a weighted correction. Yeah? So we need to correct, yeah, the value of the in each frequencies. Yeah? For example, 31.5, what is the correction for this to get dBA? Yeah? 63, what is the correction? 125, what is the correction here? 250, yeah? The correction here. Yeah? So this value, yeah, we can get from this table. Yeah? Okay, let's look the table here. Okay, here. Okay, the table. Can see here for the 31.5, yeah, the correction is 39.5. Okay, at 63, we have 26 minus 2, minus 26.2. Yeah, so don't bother about the other value. Yeah, we just bother what we want to correct. Yeah? For example, our reading is octave band. We need 31, 63, 125 until 8,000. Yeah. So now we need to find only what we required. Yeah. So 800, we need, the correction is minus 0.8. Therefore, after you after we have identified the weighting, yeah, just put it in this line, in this row. Yeah? Okay. Then, how to do correction? Yeah? It's simply added arithmetically. Yeah? Just add 124.5 add with minus 39 point, not add, yeah? Just, okay, just edit. Yeah? Sorry, edit. 124.5 minus 39.4. 120.5 minus 26.5. Yeah? You do it one by one. Yeah? 105 with 10, we got 100.5. Yeah, this one, 84.5, add with this one, 85.7. 87.5, yeah, add 1, so you got this. 77.5, add minus 1.5, you got 76.4. Yeah? Meaning that we need to add this arithmetically. Okay? So you get the new reading. This new reading is in dBA. Yeah? So this reading, it's, you know, by finding this reading, we have concerned the human sensitivity. Yeah? Therefore, now our compressor, for each octave band, it's got different reading. Yeah. Okay. From the original, the maximum is at 31.5, right? 31.5. But when we concern about our earring, it's now the 250, yeah, become the dominant one. Yeah? According to our ears, 104. All right. So to get the single reading, yeah, the single reading of this, yeah, simply added this one, but not arithmetic. Must remember that we must add log 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 logometric. Yeah? You need to use this equation, yeah, using the log addition, yeah, because this is between the frequencies. Yeah? Yeah? Between frequencies, if you want to add it together, you must use the log concept. Yeah? This one, 10 log total, but for each frequencies, you need to change it by doing LP divided by 10. Yeah? So this is the how to do the calculation. Yeah? 10 log 10 here. Yeah? So the total of all this, yeah? But in terms of log, you need to change with this one. 10 to the power of this reading divided by 10 plus 10, 94.3 divided by 10, so you got 9.43, yeah, and so on until 8,000, yeah. So you got now 109.11, yeah? So the reading now is 109.11 dBA, yeah. So from this value, yeah, we can classify, yeah, this is very high compared, yeah, compared with the our regulation in DOE. Yeah, we will look later on this one. Yeah. Okay, so this is how we obtain the dB to dBA. Okay, another example is that this is the common scenario in the construction workers. These workers, they drill, they drill, they are doing drilling activity. Yeah, so meaning that this activity will produce sound. The sound can be measured in octave band or 1/3 octave band. Yeah. Okay, so in order to avoid these workers from getting hearing damage, yeah, so they need to use the protector, yeah, the protector here, ear muff. Yeah. So the ear muff, yeah, when you buy ear muff, the manufacturer will give you the noise reduction, yeah, the noise reduction together with the attenuation. Attenuation means how big the sound can be observed, can be absorbed by this device. Yeah, it got actually in this ear muff, it got like a spongy material. It and also metal here to cut the sound from in through the ears. Yeah? So these protectors will attenuate. Yeah? The reading, the attenuation reading usually will be given by the manufacturer. Okay, let's say, yeah, the reading of the activity, yeah, the activity here, yeah, the reading, yeah, is given here. At 63 hertz is 91, 125, 104. Yeah, look at here, it is in dB, yeah? Meaning that this reading is Z weighting, or have not yet considered the human ears sensitivity. Yeah, so you need to change this to the A weighting, similar to the previous example. Look at the table. Look at the table here. Table given here. Yeah, it start from 63. So don't bother with this one. Yeah, just consider what given, data given. 63, the weighting is 26. The correction is 26.2. So put it here, 63.2. What is it? 63, 26. 26. 1 to 5 is minus 19, and so on. So again, just to get the A weighted, yeah, to our ears, Therefore, we just combine it together, combine these two readings. 91 combined with minus 26, we got 65. 14 combined with 16, so you got 88, and so on until 8,000 here. So this reading is in the particulars in specific octave band. Yeah? So we need to combine later. Yeah. Okay, mean protectors. This is the attenuation. This one, 65, 88, the reading A-weighted is actually produced by these activities. Activities when we concern with the human hearing, hearing. Here, 65 and so on. We can see that at 2 to 4,000, 1,000, 2,000, 4,000, it's got the highest value here between these two, the 2,000. Therefore, when we buy earmuff, please have a look at this value. It must has the earmuff must have the highest attenuation at this frequencies. To attenuate this, now we can see that the maximum happen at 500, 1,000, 2,000, 4,000, 8,000. Therefore, when we buy earmuff, we need to consider this reading. This reading 250 and above. Okay, for your information, according to the DOS, workers cannot be exposed to 95 dBA within 8 hours. If you work in construction site, for example, if you work 8 hours, so you cannot expose more than 95 dB. Therefore, to avoid that, you need to wear earmuff that can reduce. So the total 8 hours must be less than 95 dB. Therefore, for these workers, we need to wear mask, earmuff, not mask, earmuff, that that has the reading that can be attenuate reading at 500 to 8,000. For example, mean protector attenuation here at 500, it can attenuate 20, 25, 29, 32, and 29. Attenuate means absorb. Therefore, the final that the workers can hear is this line, a weighted protector SPL, meaning that this is the without. If the workers do not wear anything, they will hear at 63 hertz, 65, quite low, 21, 25, higher, 88 dBA, 250, 91. It's become higher and higher as the frequency higher. Okay, when the workers wearing this with mean protector attenuation, finally, what the workers hear in his ear is only maximum 83, 83 at 1,000, which is below than 95. So it is the workers now, exposed to the sound that lower than permissible at workplace. So this example shows you how we can apply the concept of sound, the physical of sound in hearing protection for the workers, and also in developing of earmuff. Okay, next is the sound propagation. Okay, what is sound propagation? As you can see here in the diagram here, okay, let's say we have I show you here one example. I think this is a good example. Okay, this is wind wind turbine. Wind turbine is the new technology for the producing energy. So this wind turbine, when it rotates, it will also produce sound. The sound is as high as 105 dBA. Not B, this is D. This is typo error. 105 dBA. It's very loud. It's similar with the lawnmower. Lawnmower cutting the grass. The sound power of the wind turbine is similar with has the same intensity as the lawnmower. When it's meaning that when you measure at 1 meter, this is the intensity of sound power. Okay, but the power of the sound, the source, they produce the sound 105 dBA. The sound will radiate. It will propagate. Okay, it will propagate, and reduce as the distance increase. It will reduce. So the reduction is not linearly, but it is I think 1 over r square. If r is the distance, the reduction is 1 over r square. The reduction of sound is 1 over r square. R to the power of square. Meaning that if we sorry. Meaning that you can see here the line, this line, it's curve. It's a polynomial. Inverted. The curve, this one curve is representing 1 over r square, meaning that it's not linear. It's not linear like that. Reduced linearly, it's not linearly, but it is polynomially reduced like that. Okay. You can see here. Usually there is a residential. So in before this tunnel established here, usually we will do EIA. We will do the prediction before the construction of new facilities. For example, in this case, wind turbine. Before wind turbine is developed, is constructed here. So usually the local authority, or the government will ask the engineers or the environmental engineers to predict, what is the impact of this wind turbine on the the residential, the nearest residential here. So what we need to do is that we need to predict the propagation. So the next lecture is we will study how the source propagate away from the source. So from this diagram, it shows that the propagation is not linear. It is 1 over r square. So you can see here the wind turbine, become reduced with 1 over r square, and finally reach to the residential with the reading less than 50 dBA. Why less than 50 dBA? I think most of the regulation in the world, the regulation at the residential is is that the LAEQ or the LP or the sound level at the residential must be less than 50 dBA. Yeah, that is acceptable. That is not, produce annoyance to the residential. Okay, so that is the how the a noise source propagate. Yeah, so you can see here it propagate, yeah, as the distant farther away from the source, it become diminished. Yeah? Okay, now, so the noise source, before we calculate the propagation, let us see how the the physical of the sound. Yeah? So at the source, we call it, just now you have understand, yeah? We have the sound power. Yeah? Sound power or the intensity, yeah, it's is equal sound power divided of surface area of the radius. Yeah? Okay. Um, the noise source, yeah, it propagate spherically. Yeah, you can see the diagram here. Yeah, it will produce sound spherically. So the intensity of the sound is equal sound power divided by the area of the this propagation. Yeah, the area of the propagation, or 4 pi r square. Yeah, QW divided by 4 pi r square. Q is the watt. Yeah? Just now I mentioned to you that power, yeah, also can be, it has a unit watt or dB. Yeah? If it's already in dB, we don't need to this equation. But if given is watt, then we need this equation to get the dB. Yeah, so don't worry about this. Yeah. Okay, so Q means physical. Q means the factor. Yeah. For the type of radiation, if the source, yeah, at above the ground, yeah, so Q is equal to 1, meaning that the propagation is spherical. Yeah, so Q is equal to 1, so you can get LP, yeah, log I here, replace I into this equation. Okay, so this is the equation. So I don't want to show you the derivation. Yeah. So this is the equation that we need to you need to understand, is that the pressure, for example, this is the wind turbine, yeah, with the sound power 64, yeah, with the distant R. So the LP here, yeah, the sound pressure outside the house is equal LW minus 20 log 10 R minus 11. So R is the distance, yeah, the distance here 100 feet. Yeah? Diagonal here, diagonal distance. Yeah? So let's look the example. Okay, so calculate the intensity and sound pressure level in dB of a sound at distance 10 meter uniformly radiated sound 1 watt. Yeah, if we have a one, yeah, let's say we have a, if we have a source, yeah, 1 watt. Yeah, the source is above the ground. Yeah, the source is above the ground, and the distance is 1 meter. Yeah, 1 meter. 1 meter. Okay. This is the source. The source with 1 watt. 1 watt. Okay. So what is the what is the intensity? Sorry, I need to. Where is my cursor? Sorry, I lost my cursor. Okay. Now we have from this question we have a source 1 watt. The power of the source 1 watt. It is located above the ground. Yeah, above the ground. Above the ground, not mentioned. Yeah, but it is located above the ground. Yeah, this is above the ground. And then calculate the intensity. Yeah. So what is the intensity of this? Yeah. Okay. Calculate what is the intensity of this source? This is the source. Yeah. We have above the ground. So what is the intensity of the source? Intensity. So we have the formula. Since it is above the ground, so we use this formula. I is equal QW divided by 4 pi r square. Why 4 pi r? Because this source will radiate hemispherically like this. Okay, it will hemisphere like this. So we use this formula I Q W divided 4 pi r square. Okay, so by assuming Q is equal to 1, since it is above the ground, so Q is equal to 1. So you got the value, this one, 3.97 for R square, watt per meter square. Yeah? R, you replace R is equal with 1 meter. Yeah? R is 1 meter. Okay. And then for sound level at 10 meter, yeah, just use this equation. Yeah. Dan juga dalam kita punya structure masukan kita nak masuk lagi. Kalau misalnya kita nak masuk, kita kena request dalam kita punya kalau director cadang kan. Okay, this is second example. Example 4, LP, yeah. So okay, let's say we have the diagram before with the sound power level. Yeah, this is sound power level because it is the sound pressure near to the source. So we assume it as sound power level LW. Yeah, by using the formula given just now, LP is LW minus 20 log 10 R minus 11. Yeah, so just put it the value here. The distance 100 feet is equal 31 meter. So 100 feet is equal 31 meter. 100 feet, it is equal 31 meter. Yeah. So you just replace 31 meter in this equation, so you get 20 dBA. So outside this house, LP is 23 dBA. So okay, yeah. Okay, now okay, just now we assume that the source is above the ground, yeah. So it will radiate spherically like this. Yeah? You can see the propagation radiates spherically. Yeah. Now, if the most of construction site except the piling. Piling is above the ground, but at certain stage it will be on the ground. But other than piling, most of the constructions equipment is on the ground. So on the ground, the Q will be equal to 2. Why equal to 2? Because it will reflect back. For example, here, this is the source. The source, it will propagate like that. It propagate spherically. Okay. Sorry. It will propagate. Initially, it will propagate spherically, but then this portion under the ground, it will reflect back like that. Reflect. Therefore, we assume that Q is equal to 2. All right. Therefore, by replacing Q equal to 2, finally we have this formula. The formula LW minus 20 log 10 R minus 8. Okay. Example. Okay. Okay, a compressor with a weighted sound power level 140 dB, already weighted, is radiating uniformly over flat non-absorbent surface. Okay, calculate the sound pressure level at 10 meter and 14 meter. Yeah, this means that, let's say we have a compressor here. Compressor. Here, this is the compressor. Compressor. It is located on the ground, on the ground. Okay. The sound power have been given, So LW, we have already know what the LW is equal 140 dBA. Okay. Then, what is the LP at 10 meter and 45 meter? Okay. So now we need to calculate what is LP here. For the LP at 10 meter. And also at LP at 45 meter. Okay. Okay, meaning that the sound will propagate, propagate something like that, propagate that. Okay, at 10 meter. So what is the value for 10 meter? And then for the 45 meter. Okay. So in this case, it's not difficult. Just use the formula, because this formula -8. You can see we have two formula. The first one is -11. This one is -11. Why -11? Because the source is above the ground. So we need to -11 here. But for the source on the ground, it -8. -8. Remember that is -8 because of Q is equal to 2. Therefore, for this example, to calculate at A, 10 meter, we use -8 because of the on the ground. So 104 minus 20 log 10 R. R is 10 meter. You replace R here, -8. So you got 66 dBA. So for the 45 meter, B here, repeat again the same formula, so you got the new one. So you got the value at 45 meter away from the compressor. That is the sound pressure level. Yeah. Okay. So now you already know how to calculate calculate sound pressure level. Yeah. The calculation is very important. Yeah, for the prediction later on. Yeah. Actually, if we have a equipment on site, yeah. If you have a equipment on site like this, yeah. If you have a sound level meter, yeah, you can record it. Yeah? You can record what is the value of the sound pressure level produced by the equipment. But if you don't have, yeah, you can see the leaflet given by the manufacturer. Yeah. So what is this? The intensity? What watt? Yeah, acoustic watt? This machine has. Then you can use the formula. This formula. Yeah. This formula, and then you can get the LP. Okay. Now you already know how to calculate, yeah, the sound pressure level at certain distance if the sound power is known. Yeah. Now what happened? Yeah, if we have two sources, two or three multiple sources. Yeah. So actually, yeah, if you have more than one sources, you can get the total, yeah, by log addition. Log addition rule. Yeah? You cannot just add 6. If you have two sources, for example, from this figure, you have two people using the same machine, lawnmower. Each produce 60. Yeah? Each one produce 60. So the total is not 120. Yeah? You must remember that. Yeah. So actually, you need to use this formula using the log addition. Yeah. So if you have a sound level meter, so you can get directly the reading. Okay. Okay. Subtraction. Yeah. We also use subtraction, like equation 6. You can see equation 6 here. Just now it is addition. Addition. Yeah, if you have many sources, or you had different frequencies, yeah, in one equipment, it produce different sound pressure level in each frequencies. So the total, to get the total, you also use this formula. Yeah. But if you have also if you have a different sources, yeah, so you can total the noise level using this expression as well. Yeah. And then for the subtraction, for example, if you had if you have a machine, yeah, a lot of machine, and then you want to know what is the value from the specific machine, so you can use the subtraction. Yeah. For example, here, LP 10, yeah, divided by 10 minus 10 L2 here. For example, if you have one machine, two machine, three machine, eh? So you have total. Eh? You have the total. You have the total of three machine. You have the total reading of three machine, but you want to know one of the machine. What is the value of the sound power level, for example. Eh? Where is my Where is my cursor? It's gone again. Okay. Okay. Let's say now we have L1. We already got L1. We got already L2. Yeah. We don't know the value of this. Okay. But you know the total. Yeah? You know L total. LP total. Yeah? Let's say 100 dB. Okay, dBA. You know the total from the three equipment. And L1, you know the value L1, you know the value L2, you don't know L3. Yeah? So you can use this subtraction. Yeah? Okay. Where is my cursor again? Gone. Where is my cursor? Okay. Okay. This is example, yeah, to apply that one, the formula. Okay. If the noise from industrial equipment is measured 55 dB, okay, in the presence of background 51 dBA, what would be the noise from the industrial plant in the absence of background? Okay, let's say we measure a machine in the factory. Yeah, let's say now we go to the factory. Yeah, we measure now. Let's say we have a 55. Yeah? Here is 81.7. Yeah, let's say we have 85. Yeah? Let's say we have 55. Okay. Okay. Background L90, yeah, or LG or LBG is equal LBG is equal 51 dBA. Oh, sorry. Sorry again. Okay. Okay. For the measurement of noise, yeah, there are two type of measurement. Yeah. Okay. In a room without any machine. Yeah. Without machine, yeah, we measure the noise we measure the sound pressure level in the you know in the room. Yeah, it is called background noise. That is ambient noise. Yeah? So that is called background noise or L90, or in other words is ambient. Yeah, without noise from the machine, from the people, and so on. Yeah? It is called ambient or L background. So in this equation, in this example, background we know before the machine. Yeah, before the machine, we know the background is 51 dB. Okay, when the machine, when the machine, we put machine, and then it's operated. It's operating, then we measured, we have a 55 dBA. Yeah, 55 dBA, meaning that the total 55 dBA is equal 55 dBA. Yeah, is include the sound from sound of machine. Yeah, machine plus sound from the background. Yeah. Okay, we have 55. Okay. So now in this equation, yeah, they want us to, in this question, sorry, in this question, what the question did is that find the noise from the equipment itself. Yeah? So we need to find the sound from the machine. What is the sound from the machine? So therefore, in this case, we use the rule of subtraction. Yeah? The rule of subtraction. Yeah. L1 is equal, this L total is 55. Yeah? L 10 to the power of LP total divided by 10 minus 10 L2. This is the background. Okay, right? So if you bring this one to the left, it's minus, but we cannot just simply minus arithmetically. We must do it in a logarithmic rule. Yeah, this is the rule. This is the proper method. This is the right method. Yeah? So we get L from the machine. This machine is 52.8. Yeah? Okay, so that is the subtraction rule that we will use, yeah, in our prediction, in the construction noise for the next week. Okay, this is also another rules. Yeah, all this while we have we calculate the LW. Yeah, what happened if we don't know what LW? Sometimes, yeah, sometimes like industrial places, they don't allow us go to their premises. Yeah? So what we need to do is that we just go at the border. Yeah. Okay. For example, yeah. Let's say now we have the factory. At the factory. This is a factory. And then there is a residential area here. This is residential area. Residential area. Residential area. Okay. So, as I mentioned just now, since this is industrial area, yeah, they don't, maybe the owner of the factory, yeah, they're reluctant to give us permission to measure the sound level at the factory. But the residential here is annoyed with the noise produced by this factory. So what we will do is that we go to the nearest, to the boundary. The boundary. We go to the boundary. We go to the boundary. So they don't. So they cannot do anything because we go to the boundary. Their boundary. Go to the boundary. Boundary of the factory. So we measure the noise at the boundary. Yeah. So we get the reading. Yeah. So we get the reading. So we get the reading here. We call it as R1. So we got R1 reading. So we got R1 reading. R1 reading. Now we need reading at R2. Yeah. What is the reading at R2? Here R2. Yeah. Meaning that, okay, now here is R2. What is LP at R2? We don't know. Yeah, at R2 and LP at R2 we don't know. Yeah, but we know LP at R1. Yeah? LP at R1 we know LP at R1. Here LP at R1 we know. Yeah, because we measure outside the premises. Okay, according to this expression, yeah, we don't need the sound power level. We don't need to enter the factory and measure their equipment to get the reading at R2. Yeah, we just use this expression, that is LP at R2 is equal LP at R1 here, yeah, minus 20 log 10 R2, the distance R2 divided by R1. Yeah? So you can get the value here. Yeah. So this is often used by the DOE. DOE, yeah. Sometimes the you know, the complaint locked by the residential due to construction noise or due to factory and so on. Yeah. So we have two methods. Whether we go to the factory and measure their sound power of the factory, or we go to their boundary and then we can determine. Yeah. We do the prediction here. Yeah. Here at the LP at the R2. Yeah. This expression is important during the prediction stage, meaning that before we construct, or before the before the factory constructed, at planning stage, for example. Let's say there is a new factory. Let's say it's a cement factory operated near to the premises. So of course, before they operated, before they develop, before they construct the factory, they need the local authority they need to send the report, the application, application to the local authority for their intention of developing the or to construct the cement factory. Yeah. So the in their report they must include the EIA report. Yeah. In EIA report, one of the aspects that we consider is that the noise that produced by the factory. Yeah? So in this case, since the factory is not exist yet, and the residential also have not yet experienced the annoyance. Yeah? So what the engineers can do is that the engineer, the environmental engineer, when doing the EIA project, they must go to the other factory that has been established, the similar factory. They can measure the noise from the factory, and then they can use that data, the data obtained from other factory. Yeah, we use that data to predict the new factory. Yeah? What is the impact to the residential? We can calculate by using this expression. Okay, for example, now we go to the example. Okay, let's say we have this is just to show you the application of that expression. If we have a sound level given by a compactor, this is a compactor, yeah? Compactor, let's say we don't know the sound power level of the compactor, yeah, or maybe it's too dangerous to go near to the compactor. So we measure using this sound level meter. Yeah, we measure at 50 meter. Yeah, when we measure at 50 meter, we get the value at 50 meter, 75 dB. Then you can predict at any distance. Yeah? For example, here at 800 meters away from this compactor, yeah? By using this expression that I mentioned just now. Yeah? So this is the direct application of the formula. Yeah? Okay, that is the physical theory, yes? Physical of sound. Okay, any question? Any question? Is there any question? Muhammad Saiful? Muhammad Saiful Islam, are you there?
Yes, doctor, I'm here.
Yeah. Do you have any question?
So far, no. I think I need to study, then I can
Okay.
good understand.
Okay. All right. Okay. Now, how can we apply our theory of sound into noise management? Yeah? Noise management in construction site, in traffic noise, in problem sound in room. Yeah, for example. Yeah, so how can we apply them in our the in order to reduce the sound. Yeah? So before we go to the management, now let's look the effect of sound. Yeah, this is the effect of sound that obtained by Chen 2017. Yeah? So actually, it has acute effects. Acute effects. The first is decreased sleep quality and quantity. Yeah? So let's say if you are staying near to the construction site, yeah, in the activity operating until late night, of course, your sleep quality, sleep disturb, yeah, the quality. You cannot have a sound sleep, yeah, deep sleep. You cannot get that. The quantity maybe only able to sleep after they are stop the operation, yeah. Okay, so this the main effect is the decreased sleep. Also increased annoyance, disturb, stress. You can get stress, distraction, and temporary change in hearing. Yeah. So, for example, just now we you have seen that the loudness. We can, our ears can only receive the highest is 120 dB. If you got that more than that, larger than 120 dB, you can get temporary change in hearing. Yeah, and this temporary change may become permanent hearing loss. And also you can get ringing in your ears. This is particularly for the construction workers. So for the work, and also engineers. Engineers may experience this. Our research last time had we will share the data next week. How not only the technician on construction site but also engineers can get the hearing loss. Okay, so there are also chronic effects. Chronic, it's result from the sleep. Yeah, your sleep. When your sleep disturbed, then you will get, hypertension or high blood pressure. Yeah, your systolic, dystolic is not in order. Usually your blood pressure is between 80 to 120. Now maybe you can get 140, 150, something like that. Yeah. Okay, and then for the school children, yeah, it will reduce learning, productivity, for the teacher, because of uneasy, and also it will disturb your hormone. It's called endocrine, your hormone in your body. Yeah, it will also disrupt and it will lead to heart disease. It's long term. This is long term risk, because noise is not it. The effect is not direct. It is cumulative. You cannot feel that time. It's, let's say, you got cut using the knife. You got cut. Yeah, you can see the wound. Yeah, but for the noise, you cannot see, but it will, you know, it will accumulate, yeah, until, okay, it's getting worse. Suddenly you get hearing loss and heart disease. Okay, it's not only heart disease from the research also, yeah, research in the West, it also can cause you Alzheimer. Yeah? So these figures is Environmental Protection Agency 1981. It's also, yeah, the noise, yeah, it change your hormone. Yeah? When your hormone change, it will also disturb your cholesterol level. Cholesterol. Yeah? If you got higher cholesterol, yeah, your you know, you will get hypertension and also the heart attack, something like that. So everything will be disturbed. Okay, so therefore, in Malaysia, yeah, we have a special guideline. We call it Guideline for Environmental Noise Limit and Control. Actually, this is the second revision. The first guideline was established in 2004. Yeah, actually, the concern about noise in Malaysia is quite new. It start early 2000, yeah, 2000, early 2000, yeah, 2001, 2, 3, and 4. Yeah. Before that, we don't have this special guideline. We refer to the UK, we refer to the US, and we refer also to the WHO guideline. And until a lot of complaint, yeah, due to construction noise, yeah, so traffic noise. So the Department of Environment have formulated and they have gathered the guideline 2004, and recently they have amended the new one, 2019, and you can go to the link that I have provided here. So this is the new guideline, yeah. Okay, in this guideline, it has a scope, purpose, legislative, noise limit, yeah, noise measurement, how to do the measurement, monitoring location, noise source to be measured, record keeping, yeah. If you if you are doing environmental impact assessment, this is very important. This guideline, noise planning, noise mapping. Yeah, last time they don't suggest noise mapping, but now noise mapping is very important. Yeah, in the current guideline. Yeah, noise mitigation and glossary. Yeah, so you can see here. Okay, lot of colorful measurement. Yeah, here. Just now I teach you how to calculate the LP. Yeah? So to get this map, meaning that you need to do many calculate. You need to repeat calculation, yeah? With respective to the distance to get the contour. Or you use we can use the software. Yeah? We have a free software. I will show you next week. Yeah, but in our syllabus, we just using the manual. Yeah, since we are now facing the pandemic. Yeah. Okay, so this is the example of the the extended of the theoretical of sound that you have learned just now. Yeah, so how beautiful, yeah, the mapping. Okay, so look at this. Yeah, okay, so this is the construction site. Okay, so normally in the EIA, one of the aspect is the noise concern. Yeah? So you need to propose, you need to give the noise contour in your report and propose the mitigation required, so that people that live near to the construction site will not disturb. Yeah. Okay, so this is the example given in the guideline. Yeah? In guideline also they give us the how to calculate. Yeah? Okay, now this is the recommended permissible sound. Okay, this is the recommended. Yeah? For example, in this we call it first schedule. Yeah? For example, low density residential, yeah? School, university, hospital, mosque, yeah? Church, and so on. Yeah, it must has the level from 7 to 10. LAEQ means average, yeah? Average LP from 7 a.m. to 10 p.m. Yeah, 55 dB or less. Yeah? So if, let's say, the school, yeah, experience greater than 55, between this range, they need to provide something mitigation. Yeah? For example, noise barrier, you know, noise barrier. Yeah? Basically noise barrier. Yeah? And at night, from 10 to 7, it must be less or equal than 50 dBA. Yeah? For the suburban, yeah, in DOE, yeah, the area categorized into 1, 2, 3, 4, 5, five area. The first is low density residential. The second one is suburban residential. This is suburban when the density is medium, and also, for example, recreational areas. Yeah? It can be up to 60 dB. Yeah? And at night, 55 dB. Urban residential, for example, high density mixed development. Yeah? For example, in Taman University, yeah, it's urban. Yeah? Urban, yeah, plus there are factory and so on. So the level will be higher. The permissible level will be higher, 65 dBA. And at night, 60. Commercial zone. Yeah, commercial zone, for example, Johor Bahru area, yeah, 65 dB. At night, 60. Industrial zone, yeah, this is like in Senai industrial zone, yeah. So it can be up to 70 dB, and at night 65 dB. So this must be, you know, fulfilled by the, you know, if for example, highway, if highway located near to the hospital, for example, Hospital Sultanah Aminah. Yeah? The hospital, it must be categorized as low density residential, or noise sensitive receptors. Yeah? Hospital is noise sensitive receptors. So it should be, yeah, it should be, if you go to the hospital and you measure in the area of the hospital, it must be less than 55 dBA. At night, 50 dBA. If greater than that, yeah, it will, you know, induce annoyance to the you know, to the, you know, what do you call the what do you call it, the nurse, the doctor, and also the the patient, yeah, yeah. So it will disturb the patient, yeah. Okay, so in that case, if let's say, yeah, the level is higher than 55 dB, the noise barrier can be built near to the road, yeah, so that it can cut some of the noise, right? So that is the guideline. So it also has different, we also have different guideline. For example, here, second schedule. Yeah. Yeah, this one is second schedule. Okay, the third schedule, fourth schedule, and so on. Yeah? So this is we will discuss in next week. Yeah. Okay. Oh, sorry. Okay, next week I will share with you how we manage the construction noise. Yeah. So we will use the physical of sound just now. Yeah, we will apply it in how we're gonna do noise management. Yeah, next week. Okay, the traffic noise management, I will not cover traffic noise management. Yeah, but you know, as I mentioned, yeah, the physical of sound. Yeah. Here, we must study the physical of sound from the traffic noise. For example, we measure the noise near to the street, yeah, and usually we will get the spectrum like this. Yeah? We can see here, this is the result of the measurement near to the road. Yeah? We found that yeah, this is the frequencies versus sound pressure level. Yeah, we can see that there's a dominant source. Yeah? Usually when we want to treat, yeah, or we want to install the noise barrier, we will study the dominant source here. You can see here the dominant source is between the 750 to 1250, okay? 100, 1 to 50. Yeah. So this is the dominant sound pressure level induced by the traffic noise. Yeah? And according to the research, yeah, this is caused by the tire. When the tire touch the pavement, yeah, it will produce the level of noise here. The maximum at 1000, yeah, due to the tire noise. Here is due to the engine noise. This is less than 250 hertz. So for the to abate the noise from the trap, to abate the noise, yeah, we treat at this range only, from 500, yeah, from 500 to the here. We don't treat this one. This is engine. This the manufacturer of the vehicle must concern, yeah, this noise. But we as an engineer, we concern about this point, which is tire noise, tire road noise. Therefore, for the traffic noise, by the abatement, yeah, carried out by the public work department or highway, yeah, they will consider two aspects. Yeah? The first is the building the noise barrier, and the second is the source. So we can treat noise, the source, and the receiver, yeah? And also between the receiver. Yeah. Okay, so in order to treat the noise, here we have the source, we have the receiver, yeah, the receiver, and then we have the source, and in between, yeah, between the path. Yeah? Okay. Receiver, we are the receiver, right? So the source is the vehicle itself, and also The source is the vehicle and vehicles and the road surface. The road surface. Okay. So the path is the noise barrier. Okay. So we need to treat the noise. Yeah, we can reduce the noise from and annoy the receiver by using two methods to mitigate. The first is treating the source, meaning that the vehicle, we must use the vehicle that quiet, the quiet vehicle. Don't, I mean, meaning that when you buy, that's why the manufacturer, they will test the sound power of the vehicles. The vehicle must reach up to certain dB that not annoy the the resident, for example. But some some people, they amend the exhaust. That is wrong. The vehicle, the manufacturer have already confirmed with the ISO, that the vehicle that this cell will fulfill the requirement. Okay, so that is the first. You treat the source. Don't change the exhaust. The second one is by treating the road surface. Road surface, you can use the quiet pavement. Quiet pavement. The second one is to treat the path. What is the path? Is the noise barrier here. Yeah. So when the noise from the vehicles impedes, the theory is that this is the physical theory, the theory of sound. When it hit the surface, some of it will be reflected, some of it absorb, and some of it transmit. So alpha, the absorption properties is very important to reduce the noise. If, let's say, you use the the reflecting surface without absorbing, it will reflect to the road, and it will make our road even more noisy, and it will the wave from the reflection will be higher, and it can reach to the residential. It will more annoy the residential. Therefore, in mitigation of traffic noise, we need a absorbent surface, so it will absorb some of the rays, that some of the wave, and reflected some of it only. Okay, so that is the theory of the sound that can be applied in the our traffic noise management. As you can see here, the concrete that can absorb the sound better is the porous concrete. According to the research, porous concrete that contain no fine aggregate will be better, because when sound impede the when the sound, it's got a pause. When the sound hit the pause, the pause will actually the pause content of the air, saturated air. When the sun impede to the saturated air, it will vibrate, and it change the sound wave into heat, and absorbed by the wall, by concrete wall. So the larger the porosity, the better the absorption. Okay, so usually the porosity is between 15 to 25%, and it must be connected voids. Okay, according to the previous research, porous concrete can absorb 40% of noise from the vehicles. Okay, that is noise barrier. Okay, beside absorb, as I mentioned, I'm sorry, I need to erase this. besides absorb, it also permit this source going out from the wall. This is true for the noise barrier as well, or some system in the building. Yeah. So this is also important. Yeah, this physical of sound also important when we want to find the sound transmission class. Yeah? So in order to have a building with high sound insulation, we must have the wall with high STC. Yeah? When the wall has high STC, meaning that it can cut sound even better. They will protect. For example, the incoming sound is 90 dB. Yeah, so the outgoing sound is 90 dB. So the STC is 90 minus 40 is equal 50 dB. So meaning that this wall has STC 50. The higher the STC, the better the wall can cut the sound. All right. So that is the the utilization of the physical of sound. Okay, this is the example of the porous concrete just now for the wall, for the sound barrier. Yeah, so this is of the properties of the noise barrier. Yeah? So the noise barrier, yeah, when we tested under the impedance tube, yeah, we will have the spectra like this. Yeah? So don't be confused with the sound level just now. Sound level, sound pressure, also sound pressure consists of different frequencies. Therefore, the absorption of the material also consists of different frequencies. For example, this is the porous concrete. Yeah? With porous concrete with 50 millimeter thickness, you can see it has the spectrum like this. Yeah? Okay, but if we increase the thickness, the spectrum will be different. Yeah? The dominant, the dominant means the highest absorption is at the 400 hertz here. You can see maybe it is 400. Yeah? Meaning that this concrete with thicknesses 100 can absorb 85% sound at frequencies 400. Yeah? At 1000 hertz, it can absorb 40% of sound coming from the traffic noise. So this is the way how we treat noise by using traffic noise by using the wall barrier, meaning that the wall barrier should also can absorb the sound that we concern. For example, just now for the traffic noise, the important the dominant, yeah, that dominant that disturb us is at 1000. Yeah, so to treat this maximum absorption, we need material that can absorb noise at these frequencies. For example, when we use when we use 100 millimeter thickness of porous concrete, yeah, 40% of the noise at 1000 will be absorbed by the barrier. So if we use 50%, 50 millimeter, it can absorb even more higher than 100 millimeter. Yeah. So that is the physical of sound that can be used in engineering, yeah, for the civil engineering, yeah, for noise management. Okay, this is another method to treat the traffic noise by using our knowledge of the theory of sound. Yeah, we will use the open graded pavement. Yeah, dense graded, yeah, it cannot absorb the tire noise. Just now we observed that the highest noise produced by the vehicle is due to tire and pavement. Yeah. the friction between tire and pavement. Therefore, we need to treat the source. The source of noise is between tire and pavement. Therefore, when we use open graded, the noise from the tire, yeah, from the tire, yeah, from the tire. This is the tire, yeah. The tire touch the surface, and then the noise and the sound wave will go into the will enter to the pause pause given by the open graded, yeah? And it will the void, yeah? The air void, the air saturated in the void will vibrate and absorb the sound, yeah? So therefore, according to the research, yeah, open graded friction cause reduce noise further, yeah? It will up to 5 dB, if I'm not mistaken. Yeah? Yeah, here. Open graded give 3 to 5 dB quieter than dense graded. You know, even though it is only 3 to 5 dB, it is very difficult to achieve. Yeah? 3 to 5 dB is very difficult to achieve, and it is very significant. 5 dB is very significant that we can feel. Yeah? If 2 to 3 dBA, it is not, we cannot feel that. Yeah? It is not significant. So for the normal pavement, yeah, it's only absorb 2 to 3 dBA. Yeah, it's not significant, right? So for the management of traffic noise, there are two methods. Yeah, replace the current, the dense graded into the open graded, and then install the noise barrier. Yeah, so maybe only by installing noise barrier, yeah, it will sufficient to attain the DOE requirement. If not, then we need to use both method. Okay. If you go to the Kuala Lumpur, there are lots of the application of noise barrier to LRT. So this is noise barrier at Kota Damansara and elsewhere. Yeah, we have a lot of noise barrier. You can see here, noise barrier. There must be the noise barrier. This is the MRT, LRT. The train produce noise, and the noise will be absorbed by the surface inside the noise barrier. Yes, so the inside surface must be porous or soft, porous, absorb the noise. So actually the noise barrier consists of two phases. Okay. One phases is the hard surface, the other phases is the soft surface. This is soft surface. Yeah. Soft surface absorbs sound. Yeah. This one absorbs sound. This is the absorb sound, the inner surface. And the one here is the outer surface. Yeah? So, as I mentioned just now, the theoretical of sound, sound from the MRT will be hitting the soft surface, and the soft surface or the porous surface will change the sound into heat. Yeah? And then it diminishes to the hard surface. So the hard surface will protect from the wave transmit to the house here. Yeah? The receiver is the house, residential house. Therefore, we can see, yeah, the inside one is porous. If you have a chance to go to Kuala Lumpur and you ride the LRT, don't forget to take a photo, yeah, of the noise barrier. Yeah, so this is very important, yeah, to avoid this disturbance to the residential. Yeah, this is installed by the international company. Yeah? Acoustic is very special, special, special work. Yeah? And not many of our engineers know about the acoustic. Yeah? Because of that, we currently appoint a Japan company to provide this, or China company. Yeah, and the cost is also very expensive. Okay, now this is very beautiful noise barrier. This is LRT and aesthetic envelope Subang Jaya. I have never seen this. Yeah, if you are from Kuala Lumpur, then maybe you can go this place. Yeah, this is actually the tube, but it's made from I think plastic, yeah? But it can absorb. Yeah? The inner surface will absorb the sound from the LR3, yeah? That produce sound. Yeah? So this is very beautiful. Yeah? It's give a good scenery. Yeah? It's not boring. Yeah? If it is concrete, or it is a steel, something like that, you cannot see the scenery. Scenery, this is Uniqlo, this is the residential house. You cannot see the trees and so on. But this one is very lovely. The function is to absorb and also avoid transmission of the sound to the premises near to the LRT. So all of this, yeah, is a result of the application of theory of sound that you have already learned just now. Yeah. Okay. And this is the lab. We have this. This is the lab at our faculty. Yeah. If you have a chance, you can visit this. This is called Impedance Tube. This can be used to measure the absorption and also transmission loss of a material. Yeah, that is that this one. Yeah? This material can be tested. The capacity of sound absorption can be tested by using this apparatus, impedance tube. Yeah, this equipment is very expensive. Yeah? Okay, again, this is the tube. This is the sample. Yeah, we cut the sample 10 100 millimeter diameter. Yeah, for the high frequencies, we need a smaller diameter. Yeah, so we can measure up to from 50 to 6400 hertz. Okay. Okay, this is the sample that we tested. Yeah, for example, gypsum. Most of building in Malaysia using gypsum, and the absorption is very low. It's very reflective. That's why, for example, if you buy new home and your new house, what happened when you go into the house? It's got reflection, echo, echo, because the shielding does not absorb. It reflects. But if you change the shielding with the acoustic shielding, acoustic shielding, yeah, the absorption is very good. Yeah, it will, when you the room become very, when you talk, you can hear clearly, something like that. Yeah, it's good. It has a good acoustic quality. Yeah, low reverberation or low echo. Yeah. Okay, this is okay. Okay, this is last but not least. It's nearly 5 o'clock. So the physical sound knowledge also can be applied in many other areas. Yeah? And this one is the room acoustic. Yeah? Room acoustic. How? Yeah, you in a classroom, in a auditorium, in a seminar hall, and so on. Yeah, in the cinema. This is cinema. Cinema. When you go to cinema, please have a look around you, around the cinema. There are absorption. Yeah. Without absorption, this is the reflection. Yeah, the reflection will be, multiple reflection. Yeah, until you cannot understand the movie. Yeah, the the what's the music also will be reflected. Yeah? So in order to treat that, we need treat the ceiling, the wall, yeah? this the floor, yeah, and also the seat also must be sufficiently absorb the excessive noise. Yeah? But you cannot excessively treat the room. Yeah? It become dead. It become not suitable for for example, for the cinema, something like that. It becomes too quiet. Yeah? When it is too quiet, you can feel your own heartbeat. Yeah? It is not good. Yeah? So we have a method. We have a technology. Yeah? So the technology is that we're using the theoretical of sound. Okay. So I think that's it. Yeah, I think I have a lot of slide, but maybe next time. But I think it's enough for the introduction. Yeah? Okay. Okay. Any question?
No question for now, Doctor. Thank you for the introduction.
Okay. So I think we need to take attendance. Yeah. Okay. Where is the? Kehadiran. MKEM, yeah. MKEM. So we have slide in. Okay. 2 o'clock. Okay, so you can slide in now. Okay, okay, if there's no There's no question, so I think.
Doctor,
Okay.
Doctor,
Yeah.
Doctor,
Yeah.
for EKB,
Oh, EKB, different, yeah.
yeah,
Eh,
another attendance.
Okay, attendance. Wait.
doctor,
So I think you can scan here. You just try. I think.
Okay,
Okay.
can Doctor.
Okay, don't forget to download the apps, yeah? Sound Analyzer, you can play around with that. Badam, are you okay?
doctor, I have a problem in my connection. I cannot scan the attendance. It give me error.
Okay, it's okay. I will take your attendance.
Yeah, because it give me. I try a lot.
Why the line in Pakistan so bad?
Doctor, I'm in Afghanistan.
Oh, Afghanistan. I'm sorry. Oh, you are Afghanistan. Okay.
I know that here there is no good facilities.
Oh. So now you are using which facility? In your home?
Yes, I have the signal booster, everything, but sometimes the signal is very weak from the company.
But
Signal
I can,
they reduce.
but I can hear your voice clearly right now.
You can hear my voice?
Yes, very clearly.
But I'm trying to scan I'm trying again.
It's okay. I will, take your attendance. How's Afghanistan right now?
Doctor, it's good, but the situation is not good. Every day target killing, everything is
Oh,
available.
really?
Yes. Very bad situation in these days.
So, people over there, what are they doing right now? Usually, what are they doing?
Like what?
Like they are, stay at home, something like that.
No, doctor. Here they do not obey the SOPs here, but also the cases is not very high in Afghanistan.
Okay. So they are work outside.
Yes, they can work, but most of the people they can work from their homes if they have their facilities of good internet.
The killing is who killing?
Target killing, this terrorists, these people, because they are increasing these days.
Yeah, terrorists. Can you recognize the terrorists?
We cannot recognize because unknown people, they fire on those people working in the government sector.
Oh.
They are killing the people every day.
Oh, so you cannot recognize. So how
Cannot. The government has also failed in their recognizing in this, but most of the people, when they recognize, they put in the jail.
Oh.
Yes.
Oh. So they don't have the certain characteristic, like you wearing turban, something like that. No, eh?
No. You cannot recognize these people. They are coming and not in uniform like well-known uniform. They are coming in the simple uniform. They are like people.
So meaning that in Afghanistan, what important is that
peace.
Yeah, peace. Yeah.
Peace only.
Yeah.
But also they have talking in the Qatar, Taliban and Afghan government. They all started, but they didn't reach to ceasefire. Yes. Still they are in Qatar.
Okay.
And due to this, I have recorded my presentation yesterday.
Oh, yeah, I know. Yeah.
Doctor, thank you.
Okay, so in the future, so what are you going to do after you got master?
Sir, I'm working with the Ministry of Higher Education of Afghanistan. I'm a lecturer at the Paktia University.
Okay.
Yes, I have teaching experience 5 years.
Okay.
Yes.
Okay.
Doctor.
Be careful, yeah.
Thank you, doctor.
Right.
Assalamualaikum.
Okay. Assalamualaikum and selamat petang and good evening to the rest of you. See you next week. Yang lain macam mana? Okay.
Salam, thank you, Doctor.
Thank you.
Doctor, thank you, doctor.
Ya.
Dokter.
Okay. Assalamualaikum. Selamat petang.
Thank you, Doctor.
Ya.